Okay, in this video I'm going to teach you the basics of series. Okay, so we have two types of series. We have a finite series and we have an infinite series. Okay, a finite series is an expression of this form. So we have some term a sub 1 plus another term a sub 2, etc., etc., etc. So a finite series is an expression in which you're adding together a finite number of terms. Okay, so the series itself is the summation of the terms that you have listed. Okay, so an infinite series is one in which you have an infinite number of terms. Okay, so there's no stopping point. It goes on and on and on. So those are a lot more complicated, and the general study of those is left to calculus. Okay, but we'll get to see some special ones in class. In this video, I'm only going to talk about finite series. Okay, so one cautionary note, because of some of the similarities you're going to see in terms and notation, a lot of students, when they're first learning about these, confuse and try to mix series with sequences. Okay, a series is a summation. A sequence is simply a list. So it would be, how could you get a sequence if you had a series? You could just list the terms. Okay, so sometimes that's actually what we talk about. We talk about listing the terms in the series. Okay, once again, if you list the terms, it's a sequence. Make sure this is in your notes, okay? Big box around it. If you list the terms, it's a sequence. If you sum the terms, it's a series. Okay, so get that straight. Alright, so I'm going to talk about a couple of special series. Well, we have a couple of special series that have very similar names to our special sequences. So the first is an arithmetic series. So an arithmetic series is one in which the terms themselves have a common difference. Okay, so it's similar to the idea behind an arithmetic sequence. Okay, only what's happening is in an arithmetic series, the terms form an arithmetic sequence. Okay, so just to be clear, an arithmetic series is one in which the terms you are summing form an arithmetic sequence. Okay, so here we can see the first term is 1, the second term is 3, that's 2 units higher. The next one is 5, again 2 units higher, 7, 2 units higher, etc., etc., etc. Okay, so because each term forms an arithmetic sequence, the series is called an arithmetic series. Okay, so just a quick reminder about the terms of an arithmetic sequence. Remember, a sub n, the nth term, is equal to a sub 1, the first term, plus n minus 1 times the common difference. Okay, so that's the formula for finding the terms of an arithmetic series. Okay, why don't you press pause while you do this first example related to this arithmetic series. So find the sum of the first 4 terms in the series. Okay, we denote that by an S for summing with a subscript of the terms that we're summing. Okay, starting from the first term all the way to the last term. So we want the first term all the way to the 4th term, so that would be S sub 4. Okay, and so that's called the 4th partial sum. Okay, so again, the 4th partial sum is denoted by S sub 4, and that's the terminology we use, so we don't have to say this long sentence that says find the sum of the first 4 terms in the series. We'll just say find the 4th partial sum or find S sub 4. Okay, so S sub 4 will equal 1 plus 3 plus 5 plus 7. Okay, so it is 4 plus 5, which is 9, plus 7, which is 16. Alright, why don't you press pause and find S sub 5. So think about, what does S sub 5 mean? And then find it. Okay, S sub 5 is just going to be the sum of the first 5 terms. So it's 1 plus 3 plus 5 plus 7 plus 9. So really it's just what we got for S sub 4, which is 16, plus 9. So S sub 5 will be 25. Okay, so again, in general, the S means you're going to just add the first certain number of terms, and the subscript tells you which of the first terms you're going to be adding. Okay, so we have a formula for summing finding the nth partial sum of an arithmetic series. Okay, so again, if these terms here, A1, A2 through AN, if the terms themselves form an arithmetic sequence, then we can have a quick formula for adding them together, that series. So it's just the number of terms. I'll show you a specific example in a second. So it's the number of terms times the quantity first term plus last term divided by 2. Okay, so let's try it here. So we found S of 5 is 25. So let's find S of 5 using the formula. So S of 5, we have 5 terms. So 5 times the first term, that's 1 plus 1, 2, 3, 4, 5. The last term is 9 divided by 2. And so that ends up being 5 times 1 plus 9, that's 10, divided by 2 is 5. So 5 times 5 is 25. Okay, so that illustrates that it actually is true for that particular partial sum. But it turns out that it is true all the time when we have an arithmetic series. Alright, so I'm going to illustrate the proof of this by finding S sub 6. And the way I'm going to find S sub 6 is actually in the method that you would use to prove it for the general case. Okay, so according to this formula, S sub 6 should be equal to 6 times the first term, which is 1, plus the sixth term, so 1, 2, 3, 4, 5. We need to get one more term out of that for the sixth term, and we see that the pattern is 2 is being added, so the sixth term is actually 11, so the sixth term in that series would be 11. So 6 times 1 plus 11 divided by 2 is what our answer is supposed to be. Alright, so the way we do it is this. It's a pretty cool technique. Okay, so we say, alright, S sub 6, we just start writing out the terms. So it's 1 plus 3 plus 5 plus 7 plus 9 plus 11. And then the trick here is to also write S sub 6 in the reverse order though. So 11 plus 9 plus 7 plus 5 plus 3 plus 1. Alright? And so then the next idea in the proof to say, okay, let's add both sides of each. So if I add the left side of the equal sign, I get S6 plus S6. Well, that's just 2 times S sub 6. Alright, so then I have 1 plus 11, that's 12. Plus 3 plus 9, that's 12 also. 5 and 7, 7 and 5, 9 and 3, 11 and 1. So I have 1, 2, 3, 4, 5, 6 terms in my sum, which means I have 6 12s. So that means that 2 S sub 6 is equal to 12 times 6. But 12 is actually equal to the first term, sorry, this is the first term plus the last term. So that's 6 times 1 plus 11. Okay, so 2 times the sum of the first 6 terms is 6 times 1 plus 11. Again, using this, why am I doing it in this convoluted way? Because I'm illustrating the proof for the general formula, okay, which isn't always easy. Alright, so now remember we actually just wanted to find S sub 6. So we solve this here for S sub 6, we divide by 2. So that is equal to, so that means that s sub 6 equals this whole thing divided by 2, or we can write it as 1 plus 11 over 2 in the parentheses. Okay, so again, that's how you prove it in general, which is a pretty cool proof. All right. Okay, so sometimes it's actually helpful to have this other formula, which I'm going to show you. So using the fact that when we have an arithmetic sequence, the nth term, so the nth term in our arithmetic series, is just going to be a1 plus n minus 1 times d. So if I use that and plug it into that a sub n, then I have a different formula. Okay, either can be used, but you're going to use the one that follows the given information that you have in a particular problem. Okay, so let's look at what this new formula is. So this is going to be equal to n times a1 plus, substituting this a sub n with this term, this expression here, a1 plus n minus 1 times d, all divided by 2. And we can just, rewrite this here. So this is n divided by 2 times, we have 2 a1s plus n minus 1 times d. So you can see this formula here doesn't actually require us to go out and find that nth term. All we need is the number of terms we have, the first term, and the common difference. Okay, so again, this one to me is more useful if I know the first and I know the last and I know how many terms I have. This one is more useful to me if I don't know the last term but I know everything else. Okay, so pick which one to use depending on the information that you have. Okay, and this deserves a box as well. Okay, here's an example. So here I have this series, 1 plus 4 plus 7 plus 10. Unless otherwise specified, you must assume that the pattern continues. Okay, so someone would have to tell you if the pattern of adding 3 each time is broken, someone would have to indicate that to you. Okay, so otherwise you just assume it maintains that pattern. So why don't you press pause while you work on finding s sub 6. So remember, you should figure out, do you want to use this formula or do you want to use this formula? Okay, when I do this, I would rather use the second formula. Okay, so s sub 6 equals n divided by 2. So 6 divided by 2 times the quantity, 2 times a1. a1 is 1, so 2 times 1 plus n minus 1. So 6 minus 1 is 5 times the common difference, which is 3. So that's 3 times 2 plus 15. 3 times 17 is 51. So s sub 6 is 51. Just a little note here though, if you wanted to use the second one, then you would find a sub 6. So I wanted to show you that it's doable. So a sub 6, we would use the formula to find a sub 6. So it's equal to a sub 1, which is 1, plus n minus 1 times the common difference, which is 16. Okay, so you could have done the 6 times 1 plus the 6th term, all divided by 2, and you would have gotten the same exact answer. Okay, so just illustrating, both work all the time. Pick the one you like the best. Alright, so this one will go a little bit faster because I got a lot of important stuff out of the way. So a geometric series, as you might imagine, is a series in which each term, or if you take the list of terms, they form a geometric sequence. Okay, so each pair of consecutive terms has a common ratio, which is a constant. So here we can see that to get each term, we are multiplying by a half, so that's going to be an example of a geometric series. Okay, why don't you find s sub 3 for this series? Okay, so you should have gotten 5.25. So it's 3 plus 3 halves plus 3 fourths. If you do that out, you're going to get that it's 5.25. Right, why don't you press pause while you find S sub 4. Right, to get S sub 4 from S sub 3, that's the way I like to do it instead of starting from scratch. Well, we had the first 3 terms, now we want the first 4 terms. So we just add that 4th term to the 5.25, and if you do that, you're going to get 5.625. Okay, so nothing really mind-blowing there after our most recent discussion. Alright, so we do have a formula which I'm actually not going to prove here. It's going to make this a little too long. So, but there is a pretty cool, fun proof for this one. So, if you're adding the terms of a geometric series, alright, the first n terms, then this guy here is your first term, then 1 minus the common ratio to the number of terms divided by 1 minus the common ratio. Note that r can't be equal to 1 if you use that formula. Okay, so if r is 1 and you have a finite series, then you just have to do it out another way. Actually, let's take a look. That would be fun. Let's take a look at that. Okay, so if r were 1, so like for example, if I had, say, suppose my terms came from 3 times 1 to the n minus 1. Okay, so my terms would be when n is 1, I get 3. When n is 2, I get 3. When n is 3, I get 3, etc., etc., etc. So if if r is equal to 1, then it's just going to be however many terms you have, then each term is going to be the same. So that would be 3 times 4, or 12. Okay, so that's what it would look like if r were equal to 1. All right. All right, for this series here, why don't you find S sub 100? Okay, so it's going to equal the first term, which is 3, times 1 minus, you'll notice this, you should always check that it's a geometric series before you actually use the formula. So it's 3 times 2 is 6, 6 times 2 is 12, 12 times 2, 24, etc. So that is a geometric series. So it's 1 minus the common ratio, which is 2. Okay, so that's your multiplier, to the power of how many terms we have, divided by 1 minus the common ratio. Right? And if you do that out, you're going to get that it is around 3.8 times 10 to the power of 30. Okay, the last thing I want to briefly touch on is is sigma notation. So sigma notation is a shorthand way of writing a series so that you don't have to take up all this space. Okay, so unfortunately in mathematics, when we have notation which is supposed to simplify things for us, sometimes it's actually a little bit more complicated at first when you're getting used to it. Okay, so using sigma notation, okay, so that's for the Greek letter sigma, capital sigma. So you're going to see a capital sigma here. You're going to see below it, you're going to see some little letter like K. So K is used a lot, I is used a lot, J. Okay, so some letter there called the index of summation, and it's going to be set equal to something. Say, lots of times it's 1. Okay, so that is called the lower limit, and then we have some number up here, say maybe 5. Okay, and that's your upper limit. So you're going to see, like I said, you're going to see this kind of thing, and then what you're going to see here is a formula. So maybe it's 1 over k plus 2. So this right here is giving you what the terms are themselves that you're adding. It's telling you how to compute them. Right, so the way you would write that out, so again, this is compact notation for a series. So the way you figure out what your series actually is using this formula. You start plugging numbers into it. So what numbers do you plug in? You start at the number down here. So that's going to be 1 over 1 plus 2. Plus, now you plug in the next number. So you started at 1, now plug in 2. So 1 over 2 plus 2. Then 1 over 3 plus 2. 1 over 4 plus 2. 1 over, the last term is when you plug this number in here for k. So 1 over 5 plus 2. So if you add all those terms together, that represents this series here. So we read this as the sum as k goes from 1 to 5 of 1 over k plus 2. Okay, so the sum as k goes from 1 to 5 of 1 over k plus 2. So lots of times the hard problem actually is if somebody gives you an expanded series to write it in this sigma notation. Let me have you practice the notation itself though. Okay, why don't you write this in expanded form? Right, so you should get, starting at k equals 1, we have 1 over 1 plus 9 plus 2 squared, so 4 over 2 plus 9. Finally, we have 3 squared over 3 plus 9. Okay, so whatever you get when you add all that up is what the sum of the series is equal to. Okay, so why don't you write this one using summation notation or sigma notation. Press pause while you try it. Okay, the way I like to do it, so I start with my sigma and I just decide what letter I'm going to use, but I don't put a starting point and an ending point, so there are in fact infinitely many possible answers to these. So I don't put my starting point and ending point until I've actually figured out what my formula here in terms of k is. So the way I like to figure that out is I start by putting down what does not change from one term to the next. Okay, what does not change is that everything has a 2 times. So it's going to be 2 times. What else does not change? Well, the exponent does not change. It's always 3. Okay, so if it doesn't change from one term to the next, it's just going to be there as a constant in your formula. All right, so now I find out the thing that is changing from one term to the next. It's what is inside the parentheses here. More importantly, 1 is 1 more, so each term inside the parentheses is 1 higher than the term before it. So that's going to indicate to you what the k goes for. So it's 2 times k cubed. And then the starting point is, all right, the first thing that we cubed was 1, so k should be 1. The ending point, the last thing that we cubed was 8, so k should be 8. All right, so this is just the sum as k goes from 1 to 8 of 2k cubed. Okay, so figure out what's the same in everything and target that one thing, that one term. It could happen in more than one place, that's going up by 1 each time. And I like to do that last. Okay, that's it.